Hello, this is a part of our lecture information on mineral formation, and this is sort of part 2 of minerals. So the focus of this tutorial is to help you understand how to describe 3 environments in which minerals form. So it's useful to think back and remember that minerals are made from atoms, and those atoms need to get bonded together somehow in the crystalline structure that makes up a mineral. So in another tutorial in another section of your book, the ways or the processes by which atoms are bonded together, or chemical bonding, is discussed. So we've got 2 examples here just to sort of get our brains going. One is the mineral halite, and you probably know this as table salt. It's made up of alternating atoms of sodium and chlorine, so it is another name for it is sodium chloride, halite, or rock salt, or table salt. And quartz. Quartz is a silicate mineral. We'll get into the mineral groups, or maybe you already have. And its unit is this triangle-shaped thing called a tetrahedron. It's sort of like a pyramid, and it's made up of 4 oxygens and 1 silicon, kind of in a cage inside, bonded to each of those oxygens. So regardless of how different quartz and halite are, they have in common that they are both minerals, and that somehow these atoms that make them up got together, bonded, and solidified to make a solid that is our mineral. It's also useful here to remember that atoms are the basic unit of matter, and they're made up of the nucleus that sort of resides in the center area of the atom, and the nucleus has the protons and the neutrons that you've heard of before. Electrons are the negatively charged particles that don't really sit in the nucleus. They are not allowed in. They have to sort of sit on the outskirts, and they orbit or circle around in kind of a field around the nucleus. And it's the electrons that actually cause the chemical bonding. We're not going to go into chemical bonding in this tutorial, but we want you to realize that chemical bonding is linking atoms together by sharing or transferring or some other relationship where electrons are moving around and causing the whole atom to become connected to another atom. I have a question for you, again, to get your brain going on how minerals might form. An important way to think about this is to consider that minerals are solids. So minerals are going to form in different ways. In our experience, it's 3 main ways, and are going to produce solids. So which of these processes makes a solid? Pause for a moment, take a look, and pick the number you think there are. There's actually more than 1 here, so that's a very big hint. There's more than 1 correct answer here. All right, so what did you come up with? Hopefully you came up with crystallizing or cooling magma, so molten rock, that would be A, is a process that makes a solid. Precipitating from water or crystallizing out of a solution of water where something is dissolved in it that is not stable, eventually becomes a solid. And E, rearrangement of atoms due to high temperature and or high pressure. This is going to end up being discussed when we work on metamorphic rocks, but all of these produce minerals, which in turn can make rocks. So let's look at a description and a visualization of what's happening when minerals form by precipitation. By precipitation, we don't mean rain. What we mean is the formation of a solid from ions, that is charged particles, either, well, they're not going to be electrons in this case, but they are atoms that are naturally charged, and they've just called ions, that are dissolved in water, and that over time that becomes an unstable configuration. That is, the water cools, it cannot hold as much of those dissolved ions, or it just becomes too concentrated. So let's take a look before precipitation happens and then after. So before precipitation happens, on the left-hand side, the description is we've got basically a box that we're seeing has liquid water in it, and there's a magnification. That is, there's a little dot, and then it's like trying to show a magnification of that. We've got some different colored atoms and molecules in there. So we've got water molecules, we've got chlorine atoms, which are ions, and sodium atoms. And those ions, chlorine and sodium atoms, are basically sitting around attaching to some of the water molecules, but otherwise are dissolved in that water. So the whole thing is liquids here, there's no solids. As conditions change, there can be an overconcentration of those atoms for the conditions that allow them to be dissolved, and the situation changes so that those atoms are actually more stable as a solid. And so what you end up with then after precipitation is the sodium and the chlorine become locked together into the mineral halite, and they make a solid. So we've got some new minerals here. These look like salt cubes, which is exactly what they are. And you can see that the green and the purple ions or atoms that were once sort of floating around in the liquid are now organized in a really organized pattern, locked into an organized crystal structure. So the punchline is that precipitation happens often when water evaporates that contains these solids. Precipitation forms minerals that often become sedimentary rocks. So this is a process that commonly happens at or near the Earth's surface. A second process of the formation of minerals is by solids that cool and crystallize out from molten rock. So same idea, off to the left we've got sort of the before, and as we go right we've got the after we have minerals forming into a solid. So off to the left we have silicon tetrahedra. So you might recognize these from our very short description of quartz before, and in fact these could be locked together, these individual little pink and red molecules, or atoms making up the molecules. Those could be locked together into a larger crystal structure that makes the mineral quartz, but right now they're actually not bonded together into a larger unit. They're just the silicon tetrahedra, which is also called silica. So silica, or the silicon tetrahedra, those molecules are part of a liquid. There aren't any solids in the most left-hand image. The silica is not bonded to other elements in the melt or the magma, two words for the same thing. As that magma, which is hot, begins to cool, those atoms are not stable staying in solution. That is, they're not as stable being part of a liquid as they would be as part of a solid. So those minerals start to form into more organized structures that we would consider solid minerals. As the magma cools completely, then nearly all the atoms and molecules that make up that liquid, magma, or melt have bonded with each other to form crystals of different minerals. And I say nearly all, as we see the quartz in the upper right-hand corner. It turns out that some atoms, some elements, don't bond easily to form solid minerals, but instead form gases when they're put in the situation. Oxygen can be one in either place. Carbon tends to form a gas instead, as some examples, and the element sulfur can do the same thing. It tends to form more of a gas than a solid in these situations. So we're not going to see, in most cases, in a rock that cools from magma with minerals in it, we're not going to see anything that contains sulfur because it is much happier, much more stable being let off in a gas form. So the big picture here is that these processes of magma cooling and then crystallizing, that is becoming solid rock, from a liquid form or a melt, this forms minerals usually within what we consider igneous rocks. And so this can happen at Earth's surface like lava or within the crust. So it can be miles underneath Earth's surface and still form. But we consider this a process that happens in the crust. Our last main way minerals form is by rearrangement of atoms that are sort of in a pre-existing rock into new, more stable minerals while they actually remain solid the whole time. So there's no melting and there's no dissolving in this scenario. So we have an example on the left-hand side of a mineral that's called kaolinite. Kaolinite is a very common mineral towards Earth's surface. It makes up the rock shale. At least it's one of the minerals that makes up the rock shale. It's known as a clay mineral. And if you can think of clay like modeling clay or like a clay mask, actually a lot of that is kaolin or kaolinite. So this is a stable rock at Earth's surface. And as temperature and pressure conditions increase, so say this is a rock that's actually put under more temperature, pressure, higher temperature and pressure conditions, maybe it's subducted in a convergent plate boundary or a hot magma comes up next to it, that can actually make those atoms in that mineral unstable in its current configuration. Basically there's too much energy and those atoms don't stick around in that kaolinite structure. Instead, what's more stable is they're forming into a mineral called muscovite that you're going to spend a lot more time with and get to know over a lot of the rest of this class because it's in most kinds of rocks. So the atoms that made up the kaolinite, due to the increased temperature and or pressure, rearrange themselves into a more stable configuration as muscovite, and it's in response to that temperature pressure condition. So basically we have the same atoms involved, but now they're rearranged in a different pattern, a more stable pattern that makes a different mineral in this particular case. So this tends to happen in metamorphic rocks. So this is usually not happening at Earth's surface, but within Earth's crust under some unusual pressure and temperature conditions. All right, so we're going to use some of the images from earlier pictures, basically, and try to see if we can have you think of what processes go with these images. So, for instance, A is showing hot molten rock moving to solid rock, and that's the process we're talking about. Whereas B is moving from these solid halite crystals to being dissolved in water. All right, so take a few minutes, take a look at these 4 scenarios, 4 processes illustrated by these images, and come up with the best example, which ones, or best answer for which of these processes create minerals. Okay, how did you do? Hopefully you came up with A is a process that creates minerals and D is also a process that creates minerals. So what would the process name be for A? If you came up with cooling and crystallization from a magma or a melt, that would be a good geologic answer. How about for D? If you came up with precipitation, that would be the best answer for this. So the process of precipitation with dissolved solids turning into, or dissolved ions turning into a solid mineral, that is a process that creates minerals. So nice job. So let's go back to this question we asked before. We asked it before in terms of what creates solids, and in fact it's the same idea. What 3 processes form minerals? And you probably already guessed, because minerals are solids, these are natural processes that occur that create solids known as minerals. So cooling magma, precipitating from water, and rearrangement due to high temperature and or high pressure.